Okay, so this is section 14.7a, video number 2. So last time we talked about relative max, mins, and saddle points. So this time we're going to talk about absolute max and mins and how to find those. So let's do a little refresher. If we had something like we would have in Calc AB, you might have something that looks like this. Where this is our function, this is A, this is B, so we'll put an A out there, put a B way out there. So now what we have is a closed curve where the critical values that you have are going to occur at maybe here, looks like maybe there, and then of course you've got your endpoints. And in order to find the absolute max of something, it is literally just the highest value. So the absolute max is literally the highest value of the curve. And in this case, that looks like that's going to occur at A. So f of A would be the highest value. The lowest value looks like it's going to occur, and we'll call this C because we have to label it something. So the absolute min is the lowest value, and that looks like that's going to be f of C. So in this case, we didn't have our absolute highest value at a critical point because the critical points are only going to be the little red dots. The endpoints are not really critical points, they're just endpoints. So the one thing you had to do was check critical points and endpoints to find maxes, absolute max and absolute mins. Okay, it's a similar concept in 3 dimensions. So we're going to have our space floating up here and doing whatever it's doing. And specifically, this space is going to have a domain, which if we were to project this down into the XY plane, the domain would be some kind of a rectangular region, or it could be a square, just depends on what it looks like. But the absolute max or absolute min of the surface is going to lie above that rectangular or square region. So we'll say the absolute, keep hitting the eraser when I don't want to, absolute max or min of the 3-dimensional surface here is going to be above the rectangular region. So in order to actually find the absolutes here, like before, you have to check the critical points, because you very well could have critical points someplace in the interior of this thing, right there, maybe up here is a critical point. As long as it's someplace within that region, you could have critical points. But then you also have to check, instead of endpoints, you have to check all of the boundary points. Check all of the boundary points. And what makes that difficult is all of this is a boundary, which means I have to check every single point along that curve. I've got to check every single point along that curve, and so on, all the way around this thing, which is why projecting this thing down into the XY plane is going to be helpful. But that's the general concept. So we have to check all of our critical points as well as all the boundary points. So now you can probably see why these could take a little bit more time to do. So let's go ahead and start an example. We want to find the absolute max and absolute minimum values of f on the set D, where D is going to be the projected domain, if f of xy is x squared plus y squared plus x squared y plus 4. Our domain is given to us as the absolute value of x is less than 1 and the absolute value of y is less than 1. I should say less than or equal to 1. So the first thing you probably want to do here is at least sketch your domain. Well, basically, this is saying that all the values, absolute value of x is less than or equal to 1 is the same thing as saying x is in between -1 and 1, and likewise for y. So our domain here is going to be a square region, assuming I could draw that, but that's not a square, but it's supposed to be a square. That's 1, that's 1, that's 1. Excuse me, that's -1, that's -1 there. So your domain is that region right there. So let's start off with the easy part. Well, the easier part, the part that we know how to do. Let's find our critical value. So we're going to follow the same process that we did before. We need to find the partials. Partial with respect to x here is going to be 2x plus 2xy. I'll have to set that equal to 0. And the partial with respect to y is going to be 2y plus x squared, and we have to set that equal to 0. Got to solve one of the two of these things for a variable, and it doesn't really matter which one. Actually, we don't have to now that I'm thinking about it, because if you look at fx, you can factor a 2x out of there, and then you're left with 1 plus y equals 0. Well, that means that x is going to equal 0, or y is going to equal -1. All right, well, if x equals 0, we can plug 0. Here, let me use a different color. If x equals 0, we can plug 0 into the fy function. We get 2y equals 0. So if x equals 0, we get 2y equals 0, which means that y also equals 0. So there's a critical point, 0, 0. If we were to plug in y equals -1, let's see, if you plug in y equals -1, you're going to get -2 plus x squared equals 0, which means x squared equals 2, or x equals the plus or minus √2. Well, the only good thing about that is that's outside of our domain. Our y's can only be within -1 to 1, so this one really doesn't do us any good. So that means we really only have one critical point. Our critical point is the point 0, 0, because that one works. So this was out, because y equals -1 does not work for us. Doesn't mean that this function doesn't have a critical point there. It's just not inside the specific domain that we're given. All right, so let's find the actual, because now we're actually trying to find max and min value. So let's find the value of this function at 0, 0. And if we plug in 0 and 0 for x and y, we should just get out 4. Okay, that should be pretty straightforward. That's the only critical value that we have. So we have a critical value right at the center of this thing, which most likely is going to be a max or a min. Just, is it going to be the absolute max or min? Well, we have to test the boundaries. So here's what you have to do. This is where it gets a little bit tedious. We're going to call this side right here L1. We're going to call the top L2, the left L3, and the bottom L4, because they're all linear components that make up these sides. The order that you put them in doesn't really matter. I just went in that specific order. It does not make any difference. So L1 is literally the line x equals 1. It's a vertical line, x equals 1, which means that that is held constant. So what I have is I have a function of 1 comma y, because y can vary. Y varies vertically. So what is my function of 1 comma y? Well, you're just going to replace a 1 for all your x's, which is going to give us 1 squared, which is 1, plus y squared, plus 1 squared y, which is y, plus 4. All right. So now this is literally just a function of y because the x's were held constant. So now when I do this, to find critical values, just like you would do in two-dimensional calculus, you're going to take a derivative. But we are taking a derivative of 1 comma y because, again, the x's were held constant at 1. So we're really just taking a derivative with respect to y. So the function is a function of y. So the derivative is 2y plus 1. And we set that equal to 0. Solving that for y, subtract 1, divide by 2, you get that y equals negative 1/2. So x was held constant at 1. The y value is negative 1/2. So what that really says is that when x is 1, y is negative 1/2, you have some kind of a critical value right about there, up on the actual function. So again, whatever the function is doing in space, that gives you a critical value when you go up to the z value. Well, we need to figure out what that z value is. So we're going to take and figure out what f of 1 negative 1/2 is. So f, excuse me, f of 1 and negative 1/2. If you plug both of those in, I've already actually worked this one out, it gives you 19/4, which is greater than 4. So we know that 4 is definitely not our absolute maximum because now we have a value which is bigger. Okay, we have to do L2. L2 is the horizontal line going through y equals 1, so it is literally y equals 1. The x values can vary, so we have a function now of x comma 1. So if we plug the 1 back in for the y's in our original function, we now get x squared plus 1 plus x squared plus 4, which is obviously the same thing as 2x squared plus 5. You didn't really have to do that part, but if it helps, that's fine. So now it's a function of x. So when we take the derivative, f prime of x1, it's going to be 4x. Setting that equal to 0, you get that x equals 0. So now I have 0 comma 1. So I need to find the function at 0, 1. And if I were to plug in 0 and 1 back into the original function, I believe we get 5. Okay, that's 2 of them. And so far, it looks like 5 is the leader in the clubhouse for the maximum, because that's the highest one I've gotten so far. So now x equals negative 1 is L3. So that's going to be a function of negative 1 comma y. So if we plug negative 1 back into the original, I'm trying to squeeze this all on here, I'm not going to be able to. Plugging negative 1 back into the original is going to give us, I believe it's 1 plus y squared, because then you have x squared, so that's going to be positive 1y plus 4. I'm not really worried about combining the constants because when I take the derivative, they're going to go away. So then we're going to do f prime of negative 1 comma y, which is going to be 2y plus 1. Setting that equal to 0, we get that y equals negative 1/2. We've already done that. We don't really have to do it again because we're going to get exactly the same thing that we did in L1. So we can just state that f of negative 1, negative 1/2. Actually, we didn't do that. I apologize. It is, however, going to give you the same thing because the x's, I believe, are both squared. Yeah, the x's are both squared, so it actually ends up giving you exactly the same y value. All right, we've got one more to do, which is L4. And that's going to be the bottom one, which is y equals negative 1. So we're going to do f of x comma negative 1, which plugging that back in is going to give us x squared plus 1 minus x squared plus 4. Well, the x squareds are going to subtract away, so that really just gives you 5. So f prime of x comma negative 1 is literally just 0. All right, so that is not actually going to give us a max or a min. Okay, so there's only one more thing that we have to consider, because we've considered everything on the lines. The only other things that we have to consider are the corners or the endpoints. We've got to consider all 4 of the endpoints, because those may or may not be taken care of by each one of these vertical and horizontal lines. So we basically just need to test those. So our endpoints are the points 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. If we were to plug those things back into our function, you would get 7 for the point 1, 1, 7 for negative 1, 1, and 5 for each one of these. Okay, this is actually a really interesting function to look at. And if I have time, I might make a supplemental video to show you the graphs of these things so you can see it. But ultimately, what that says is 7, I believe, was the highest value that we had, and the lowest value looks like it was 4. So our absolute minimum was 0, 0, 4. And our absolute maximum looks like it occurs at one of 2 points. It's either at plus or minus 1 and then 1, 7. So either the plus or minus 1 for the x value and then 1, 7 for the y and z value. But those are it. So again, as you can tell, these things take quite some time to do, because you have to check all of the boundaries, the endpoints, and all the critical points to figure out where the absolutes are going to be. As a matter of fact, this is pretty lengthy, so I'm going to come back with a third video, which hopefully should finish off the last 3.